and I've broken the presentation into three main parts on the basis that this is quite an evolving topic, and I want to try and give a really balanced approach in terms of the use of this technology in relation to its fire risk and its benefits as well. So I've broken the presentation into three parts. Part one really covers understanding context, and that's really looking at the advantages over this type of battery technology from conventional battery technology, and also how a lithium-ion battery works. Good, no thanks. Then moving on to the fire risks associated with these batteries. So what do the statistics tell us? Why does this technology catch fire from time to time? What's different about these types of fires? And also, how can we manage those risks associated with the technology? And then I've included a third section, really just to give a look ahead about how the battery technology is evolving. It's almost every month there's a release from one of the manufacturers about a breakthrough in the technology. But I think it's also always appropriate to consider that often the legislation and standards, which I'll talk about in some detail throughout this presentation, always tends to lag behind technology advancements. And we're now bringing in technology and standards after the technology is being developed, and we want to try and make sure that they're developed in unison. So just a bit of context in terms of Network Rail. So we've now entered CP7, which started April this year, our control period, which is every 5 years. And the theme of CP7 is simpler, better, greener. And the sustainability element is quite a key focus of that strategy in the route to decarbonisation. And that looks at the provision of electric vehicles, renewable energy, and reduction in diesel emissions. So this ties into the use of this technology. Why is this technology used above conventional battery technology? And I've just put some ideas down of some key themes in relation to its benefits. So much higher energy density, much lighter and compact in terms of its unit density against its weight, compared with conventional lead acid batteries, which are quite heavy. Low maintenance, so you don't get this issue of what we call lazy battery syndrome or memory effect, where it just discharges and charges to predefined levels of usage. Much better cycling periods, last much longer, and a much lower self-charge rate as well. So there's lots of benefits to this technology. I've included this because often people get confused, and especially with people being advised regarding what type of fire extinguisher to use on these types of fires. So I've included this just to give a bit of context. So a lithium battery and a lithium-ion battery are completely different. So the main difference is one's rechargeable and one isn't. So if you look at a lithium battery, its primary cell cannot be recharged, and therefore it contains lithium metal in the one of the electrodes, the anode, and therefore if the cell is exposed to water, it will react violently with water, what we call a Class D fire, a metal fire. Whereas if you look at a lithium-ion battery, its secondary cells are rechargeable, and therefore the lithium is in an ionic state, which means it's really a fancy word for an atom or a molecule which has a non-zero charge because it's lost or gained an electron. So it's not actually metal, and therefore you can put water on a lithium-ion battery fire. I'm not sure I would use an extinguisher to tackle these types of fires for other reasons, but if you look at how they tackle electric fires, vehicle fires in Europe, a lot of the time they actually will submerge the vehicle in a water container. If you look at the advice from the National Fire Chiefs Council in the UK, it's copious amounts of water. There are some standards that have been brought out recently to look at energy battery storage systems. So NFPA 855 is one standard, which was based on research from the Fire Protection Foundation in America and FM Global, and they support the use of sprinklers to control these types of fires. So you can put water on these fires. In terms of the battery itself, it mainly consists of 4 components. So you've got effectively 2 electrodes, an electrolyte, and a separator. So if you look at the cathode, which is the positive electrode, that's the source of ion. That determines capacity and voltage of the battery, and is generally a metal oxide. So typical examples of cathodes includes lithium cobalt oxide, lithium-ion phosphate, which is quite extensively used, lithium manganese oxide. And then you've got the cathode, which is the negative electrode, and that's generally carbon-based graphite coated in a copper foil. Then you've got the chemical soup, if you like, which is the liquid electrolyte, which is the flammable bit of the battery, and that helps to transport the lithium ions from one side to the other, and that's usually a lithium salt in an organic compound such as lithium sulfate fluoride. And then you have the separator, which might be a plastic polyethylene type structure, and that's to keep the electrodes separated so you don't get a short circuit. So they're the main components of a battery. And then when we're charging, the ions go from the positive to the negative side, and as they arrive at the anode, think of the anode, which is a graphite type structure, as the ions trying to find parking spaces within that structure. Intercalation, the process is called, and then when you're discharging, the ions reverse the other way. So that's the basic concept of a lithium-ion battery and how it works. The concept is the same, whatever battery you're dealing with, in this movement of ions from one side to the other, but the battery chemicals can be different. So the battery chemistry can be different, and I've just shown you a few examples of the different types of battery chemistries that can be used. So if someone said to you, I've got a battery and it's NMC 622, that's referring to the cathode, and that's 60% nickel, 20% manganese, and 20% cobalt. Very difficult to tell what these batteries are. I would say probably if we look at rail, lithium titanium oxide is being quite focused on at the moment because it's got really good security and stability. It enables fast charging in terms of performance. It's got relatively long life cycles, good resistance to dealing with a wide variance of temperature as well. I suppose one of the downfalls of lithium titanium oxide is it is quite expensive, and I've just given some examples here of what we're doing in looking at different train manufacturers and the power that you're looking at to get with lithium-ion batteries, which obviously can vary depending on the size of train, etc. So hopefully that's given a bit of context regarding why the technology is used, how it works. Now, if I go into the statistics around what are the fire risks associated with these. So information published by London Fire Brigade suggested there was about a 78% increase in fires involving e-bikes and e-scooters between 22 and 23. And that's supported by similar data from a Freedom of Information Act request, where 48 fire services responded with information. And again, they're reporting about 80% increase. I'm working with the RSSB at the moment in looking about, as an industry, how do we tackle this problem in terms of the use of e-bikes and e-scooters within stations, but also as rights of carriage on trains as well, because as an industry, we need to have a joined up approach. With those statistics, so 408 fires, etc., it's very difficult. They're actual events, but it's very difficult to determine, is the number of events proportional to the increase in the use of those types of products. And this is information I got from a global organisation called eSafe, which is based in Australia, EV Safe, and they look at statistics from around the world in terms of car fires, etc. And there is a direct correlation shown on the right-hand side in terms of the number of EV fires against the number of EV vehicles on the road globally. And there's a direct correlation there, the black being the number of fires, the red being the use of EVs on our roads. Interestingly, about 20% of fires involve the vehicle being on charge. And I think most of the car manufacturers are quite responsible. So the likes of BMW and Jaguar have recently recalled models because of concerns with issues to do with overheating of batteries, etc. So those figures could be higher if it weren't for the manufacturers recalling their cars in terms of protection of the brand, of course. Why do these batteries catch fire in the first place? And it all stems from abnormal cell behavior of some description and the phenomenon of thermal runaway. A thermal runaway is where a cell becomes damaged for a number of reasons, and it will release heat because electrochemical reaction and raise temperature. As it raises temperature, you get an exothermic decomposition of the cell materials, which then increases the rate of self-heating. And then you reach a stage where the amount of heat being generated is more than the rate of heat that can be dissipated from the battery. And then that results in a loss of stability of the remaining energy within the battery. And then you get this further propagation where you get a release of energy from the battery in a fire. And I've tried to illustrate that graphically in terms of the scales of heating, that it's this self-heat being generated that you can't dissipate it quick enough, and then you get a rise in the overall temperature, which compounds the problem. Why does this happen? Well, there's a number of reasons. It can be mechanical damage or abuse, where perhaps you've dropped a battery and the battery doesn't necessarily swell. You can have electrical abuse in terms of overcharging, causing a short circuit. Over discharging can be a problem, not using the right charging with the right battery, and you can get a number of other issues associated with that. So one of the main issues you can get is an issue of a solid electrolyte interface forming on the anode, which is a sort of surface layer that falls on the anode. And also you can get what we call lithium plating, where you get deposits of the lithium on the anode as well. And what that means, when I spoke about the lithium ions going into parking spaces on the graphite, the carbon graphite, with lithium plating and the solid electrolyte interface, they don't fit in the car parking space, so they just remain on the surface. Now, what this means, it can severely affect the performance of your battery, and it's a natural phenomenon due to the chemistry in the battery, that you will get depletion of performance over time. Because the chemical composition can be different, the range in which thermal runaway occurs can vary anything between 150 to 270 degrees, depending on battery chemistry. But with this plating arrangement, you start to get poor performance. It takes longer to charge, you lose some of the battery capacity. However, in more serious cases, you can get things called dendrites forming, and these are microscopic structures that form out from the anode, and they can form all the way to the separator, and they can puncture the separator. And once you lose separation between the two electrodes, the cathode and the anode, you end up with a short circuit and a fire. So this is a real problem, and it's exacerbated by very fast charging at low temperatures as well can actually result in poor performance of the battery. And this is one of the reasons why you get a short circuit in the battery system and you get a fire. What's different about these fires? And they are different. So if we look at these types of fires, they're actually really difficult to extinguish. And that's because the chemical reactions that happen within the battery, they can produce their own oxygen. They can reignite. So even when you think you've dealt with a fire, several hours or days later, they can reignite because they may still have some energy within the battery. And in the majority of cases, you tend to get a jet flame occurring with these types of fires, and you get an exponential fire growth compared to conventional battery fires. And I've just shown on the right-hand side there some work that was done by the Institute of Applied Fire Safety Research in Germany, where they were looking at heat release rates of e-bikes on trains, funny enough, and looking at how quickly the fire grows. If I try the link, it might work. Ah, good. So it's a 32-minute video, but if I just put it to about 15 minutes. So this was a fire they were looking at.
There's nothing coming through, John.
Oh, you can't see it?
No.
Oh, that's a shame. I'll circulate it within the presentation anyway. But the other issue, you can get vapor clouds, which people distinguish as they think it's steam, but it's actually gases within the vapor cloud, and you can get stranded energy. So these fires burn very quickly, very rapid, but they don't last very long. I've included some research that was done by Arup on behalf of the government, looking at the concerns regarding e-vehicles in covered car parks and charging as well. And this was based on some research that was done some time ago, where they looked at 6 types of cars they set alight to look at their heat release rates, etc. And again, just as the previous slide, they had jet flames occurring when they have thermal runaway, and that can be a problem in terms of lateral fire spread. So you get a much higher rate of potential fire spread laterally because of jet flames that generally sit underneath the car where the battery is. The full-scale testing, the overall fire size, so if I looked at the complete fire size of the complete vehicle, that wasn't significantly different, but the burn rate of how quickly it reaches that fire size was significantly higher with EV vehicles. In 13% of cases where the fire brigade had dealt with it, so initial suppression, the car reignited. And this is an interesting, the last 2 points are quite interesting, is that can take up to 10 times longer to extinguish a fire, and about 10,000 litres of water compared to a conventional vehicle. And you have to remember that that water's contaminated as well. So there are some environmental considerations that are appropriate to consider. How can we manage these risks? And I've just put this slide in to really show it's actually quite complex, and it's not one size fits all. There's a number of different interconnecting aspects that we need to look at. But if you try and sort of break it down to a understandable concepts, at Network Rail, the approach we take is a concept called PPI, which I developed some time ago. And that stands for prevention, because our best line of defense is preventing fires in the first place, recognizing that you can't eliminate that to zero. So it's about reducing the probability to as low as reasonably practical. What protection we put in place, And that's not a one size fits all, because that depends on infrastructure arrangements and building configuration, and the intervention, which is the human bit in terms of emergency procedures, pre-incident response plans with the fire services, etc. So when we look at prevention, thermal runaway just doesn't happen. There are some precursors to it in terms of temperature rise. So how we monitor temperature, for instance. So if you look at a lot of the car manufacturers now, they're starting to look at BMS type systems that monitor the rise in any temperature arrangements within the battery compartment itself. Off-gassing detection to shut the battery down, so you generally get the release of gases before you end up with a fire. Also trying to reduce mechanical damage, making sure we're using the right charger with the battery, trying to reduce the frequency of charging, fast charging in cold temperatures, etc. And also specifying batteries that comply with relevant standards as well. Then we go into the protection, and you've got a number of different manufacturers. I've just put one there to give a bit of context in terms of specialist storage cabinets that are fire rated from the inside. They're fitted with off-gas detection as well. They're fitted with charging if you want, and suppression systems. Storage within fire compartments within our buildings, where we've got fire separation from the rest of the building. The provision of active fire systems, so sprinklers, water mist, and other forms of detection. So Audi have just brought out a fire suppression system for their batteries in dealing with those risks. And then the final part is the intervention bit. So training of staff, pre-incident response plans, making sure the fire service know that you've got those types of risks within the building in terms of pre-incident response plans for the fire service as well, which ties into many of the aspects of the Grenfell inquiry, the phase 2 report that was issued about 3 weeks ago, where they talk about the golden thread in terms of on-site information for fire services and on-to-day management. I don't know whether people will be aware that there's a lithium-ion battery safety bill going through the House of Lords at the moment. So it's had its second reading. It's at the committee stage, and it consists of 10 clauses. I put a link within the presentation in terms that you can read about the 10 clauses, but it's really trying to control products in terms of certification. So it looks at online sales of these types of products, e-scooters and e-bikes. Also, the introduction of a conformity assessment body that effectively will give you a certificate for your e-bike or e-scooter. And also the enforcement and safety standards around conversion kits. So that's quite a key challenge. People can buy off the internet conversion kits for lithium-ion batteries where there's very little control. So I think it's a step in the right direction. Does it resolve all the problems? No, but I don't think it's a single issue. I think it's a multifaceted approach that we have to take in managing these, and of course enforcement action of how such legislation is enforced. I've included aspect regarding firefighting, because people always think the fire brigade will just come and put the fire out, and that is in the majority of cases, but it's really quite difficult to do so. There are systems on the market, and I've just given an example of one type system, Rosenbauer, which they have what they call a BESS system, which is effectively a hydraulic ram that sits underneath the car, connected into a fire hose. It's got a spike on it, goes underneath the car, it penetrates the battery compartment, and it floods the battery compartment with water. And that's really one of the most effective ways of trying to deal with it, because when you look at suppression systems such as sprinklers, it's very difficult to get water on the battery, because if you look at a electric car, effectively the floor plate is the battery, and therefore the sprinklers won't put out the fire, but it will hopefully stop it spreading, but you've still got the battery on fire. I've included this part really to talk about how the technology is evolving, because if you look at between 2008 and 2020, in terms of volumetric energy density, we've had an increase of about 8-fold on lithium-ion batteries. So there's been quite a significant move in the industry with lithium-ion batteries. But my view is they're starting to plateau about 300 watt-hours per kilogram. And we want more energy, smaller batteries to increase the range of which we can drive our electric vehicles. And when we have to charge them, we want much quicker charging. So the technology has limitations. If you look at recent developments, then they've looked at replacing the anode with which is carbon graphite with silicon type arrangement, because that has 3 times the energy density of carbon, and that can increase the battery performance quite significantly. However, there's problems with that in terms of its expansion and contraction. You have to put it under a lot of compressive stress, which does cause problems. So they've tried to sort of mix some silicon in with other types of products to improve performance. And changing the anode to a lithium metal, that really does give significant improvement. But the problem is, because of the liquid electrolyte reacting with the lithium metal, you end up with a short circuit. So one of the most promising areas of research is sodium-ion batteries. So I thought it was worth mentioning that. There are other technologies that are being looked at, such as hydrogen, potassium-ion batteries, etc. There's a whole range that would warrant a separate presentation in its own right. But sodium-ion batteries seem to be quite hopeful. One of the reasons is that the availability of the raw material. So the US has most of the largest salt deposits in the world, environmentally very friendly in terms of extraction and disposal, can deal with a wide spectrum of operating temperatures and fast charging. Why hasn't it caught on? I think there's been issues with supply chain, and also it's generally low energy density. And what I mean by that, the top ends lithium-ion batteries will do about 300 watt-hours per kilogram. When you look at sodium, it's about 150. There are views, Panasonic's just released something recently that they can match a lithium-ion battery in terms of energy density, but we've not seen that at the moment. That technology may evolve, but it's not there at the moment. It has limited application as well in terms of you can't really use it for high performance applications. So I don't think sodium-ion batteries will replace lithium-ion batteries, but it will probably complement it in terms of market availability. One of the key areas of development is the concept of solid-state batteries. You start to get significant benefit, and what we mean by solid-state batteries is changing the liquid electrolyte to a solid electrolyte. However, that by itself doesn't really do anything. It actually makes the performance of the battery worse, because the solid electrolyte is about 5 times denser than the liquid electrolyte. Where you start to get the benefit of actually moving towards using a lithium metal as the anode, because if you look at lithium metal, it has about 10 times the specific capacity of graphite, so you get a significant increase. And also the size of the battery can now vary, because to hold 1 atom of a lithium ion, you need 6 carbon atoms. So if you can remove all that in terms of the graphite, you can remove the individual layering for the cell packaging, which is a big issue, and you start to get some real benefits in terms of being able to move that forward. One major problem with the technology is you've still got this issue of cycling, of stripping the lithium metal, depositing it, and then putting it back on, and that continuously happening, which can cause problems in terms of void formation within the solid electrolyte, cracking of the solid electrolyte, and the formation of dendrites as well. So there's a number of challenges with the technology. A lot of the main battery manufacturers are working on this, and they're quite confident they'll solve that. So there has an advantages of improved safety. So not that these batteries can't catch fire, but they're significantly lesser risk because you're removing the liquid electrolyte, which is the flammable bit of the battery. You get much faster charging because you're using now a lithium metal with much higher energy density. So the reports from the University of Colorado, for instance, looking at about 450. So that's a 50% improvement, 450 watt hours per kilogram, and much longer lives in terms of the conventional lithium-ion batteries. How does it work? Well, during discharge, lithium metal is stripped to become lithium-ion electron. Then when it discharges, the volume of the battery reduces, and then during charge, the lithium ions are plated back onto the lithium metal, causing it to expand. So this constant expansion and contraction, which can be problematic, and this stripping and then depositing back on, which can be problematic as well. And I've just really shown this as an example of some of the challenges we get with the solid state technology. I think it will come to fruition. And I said manufacturers are working at resolving these issues, but these are some of the challenges we get with the solid battery technology, why it's not here now. So you get the solid electrolyte, it doesn't block, especially if you're using something like a polymer solid electrolyte, it doesn't block the formation of dendrites, which are these microscopic structures that can go throughout the solid electrolyte and effectively short circuit the battery by joining the cathode and the anode. Lithium metal is quite a soft metal, so you do get an issue of mechanical creep, which can cause short circuitry between the layers of the solid electrolyte, and also the uneven loading of the anode as well, because of how ductile it is. You can get dead lithium forming within the electrolyte, so dead spots that produce the performance of the battery. And because of this expansion and contraction, the electrolyte can become quite brittle, cracking, and then you end up with void formation as well, is a key issue. So in summation, I think as fire engineers, we have to be balanced in our approach. This technology is here to stay, and it will continue to evolve as society requires better performance in terms of energy density. And we need to consider a life cycle approach of how we dispose of this technology as well. Fires involving lithium-ion batteries are different from conventional fires, and therefore the strategies of how we deal with it should be reflective of that. I think the emergence of solid-state batteries may change our approach to fire protection and firefighting due to the inclusion of lithium metal. So you can't really use water on these types of fires because they're a metal fire. I think it's true to say within the fire industry and a regulatory perspective, we've been slow to react to the risks associated with this technology. And it's imperative that we actually learn lessons from recent events. There's a lot of synergy with Grenfell in terms of understanding how we move forward as an industry, embracing this technology and managing it. If you look at the statistics in terms of pure numbers, it's likely the numbers of fires involved in this technology will increase. Once thermal runaway has started, it's really difficult to stop, and therefore our strategies should be focused on prevention with thermal monitoring, etc., of battery performance, rather than trying to tackle the fire. You know, one of the issues with these types of fires, very fast growing, the amount of smoke that it produces as well, and toxic gases can be quite significant as well. So whilst you might have fire extinguishers that can deal with these types of fires, I wouldn't encourage people trying to tackle them, because the amount of toxic gases you get in terms of hydrogen fluoride, you get phosphorus tetrafluoride, hydrogen cyanide, etc., quite a lethal cocktail of gases which can be problematic. But I think it's important that fire professionals, we need to embrace this technology in context of its use, recognise its benefit in terms of promoting research and innovation in technology. And at that point there, I'll end my presentation. Happy to take any questions.
Thanks, John. I've got a couple of questions in the chat before we go to them. Is there any chance you could copy that link to the video that we didn't see into the chat,
Yes.
and then we can perhaps have a look at that? And if it's possible, could you send us a copy of your presentation as well?
I'll do that this afternoon.
That's brilliant. I'll take a couple of questions from myself, if you don't mind, before we start. First one is to do with, is there any guidance in terms of charging points for electric scooters and electric cycles at this present time in our guidance?
So that's a really good question. So we have a policy in relation to our stations about electric scooters and electric bikes. Generally, we try to have charging outside our stations at least 3 meters from the building. With the broader issue of bikes being used transiting through our stations, we need to have a joined up approach as an industry, because I think most of the train operating companies have banned e-scooters, but there's been quite a significant rise in fires involving e-bikes. In fact, fires involving e-bikes have overtaken e-scooters, and that might be because there's more e-bikes around being used. But I think we have to come together as an industry, because it puts our station staff in a very difficult position in relation to trying to manage these devices within stations if they're arriving on trains. And that's one of the approaches we're trying to work with the RSSB in terms of that industry approach. But to answer your question, in terms of charging, we generally require charging outside the station at least 3 meters away.
It's quite interesting, because looking at e-bikes and using them on the train, it seems to be certain makes are acceptable, but there's been all sorts of problems in the press recently about e-bikes being modified and what have you. And it's how you actually manage and control that, so that, you know, you've not got some of these bikes that have been modified actually traveling on the railway, and stop them from doing that.
You're absolutely. So we've got the lithium-ion safety bill that's trying to regulate the sale of e-scooters through accredited conformity bodies, etc. But the question is, well, how do you control that, and people buying conversion kits and what have you? So, you know, one of the things that potentially could work is, and I'm not saying we're doing this, but that this is perhaps an idea we could look at as an industry. When you book your train tickets, you register your e-scooter with a certificate for use on the train as well. Very typical. Do that with a lot of aircraft arrangements as well in terms of the aviation industry. So looking at things, how we can use technology to try and manage this risk, because it's quite difficult managing it otherwise. Will we manage it 100%? I don't think we will, but looking at making sure with the festivals that we're not promoting charging points on the train as well, and trying to make sure they're further away from festivals, so it doesn't encourage people trying to charge their bikes on the train. I was in a meeting with the RSSB about 2 weeks ago, and some of the train operating companies said that was a real issue in terms of people charging bikes on trains that they had, and trying to enforce that is difficult.
Yeah. Okay, I'll go to some of the questions that are in the chat. For rechargeable batteries, is there such thing as a kill switch, something that will neutralize the battery to prevent thermal runaway?
Yeah. So the issue is, some of the manufacturers are looking at effectively measuring unusual temperature rise and unusual voltage behavior effectively. So some of the car manufacturers are looking at that they set the temperature at X, which is a precursor to the onset of thermal runaway. So that is feasible through temperature monitoring of the battery.
Okay, next question.
Some large robotic companies are looking at that at the moment.
Okay, so the next question, what is the role of smoke extraction in these batteries enclosures? Is there a risk of explosion during the thermal runaway?
So yes, they can explode in terms of vapor clouds, etc., because you're giving off quite a lot of gas. The amount of gas will vary depending on the chemistry. So if you look at, there's always a trade-off, unfortunately, between safety, performance, and cost. So if you look at typical lithium iron phosphate, for instance, it's a very safe battery. It doesn't generally catch fire that often because of the chemistry. But it's not the best performing battery on the market. There are better performing batteries, but they inherently have greater safety concerns. So, and I think the other issue that you need to be mindful of is that whilst you get quite significant thermal propagation in terms of fire development, you do get quite a lot of smoke developing. And as I said, the cocktail of gases can be quite problematic. So if you're storing or charging these types of devices within rooms, it's better to have separate smoke ventilation to try and clear the space as well, rather than trying to use your building mechanical ventilation system, which will obviously get contaminated with smoke as well.
Okay, question from Mr. Williams. How might MSCP design need to change as the use of EV grows, if at all?
That's a really difficult question. I think, and again, if you look at the Fire Protection Association, for instance, they've got guidance out RC59 of looking at what protection measures you put in. Now, some of those measures are quite impractical, especially in existing car parks where you might be putting in 20 charge points for electric vehicles, for instance. It's not very effective to sprinkler the entire building or sprinkler the part of the building that has electric vehicles charging. And the reason being is that that requires quite large infrastructure in terms of fire pumps, sprinkler tanks, etc. But I think there are more credible strategies where perhaps you can use dedicated areas with localized suppression, and also temperature monitoring and battery monitoring of voltage, etc., that to try and prevent the onset of thermal runaway, because thermal runaway just doesn't happen. There are precursors, as I said, in terms of unusual voltage behavior and temperature rise that we can look at in terms of charging in conjunction with perhaps localized suppression systems. So things like water mist might be a credible alternative that can be quite localized and doesn't require significant infrastructure either.
Okay, next question. Could you please elaborate why water can be utilized to put out these types of fire?
Well, if you look at, because they don't contain lithium metal, because the lithium is in ionic state, e.g. it's lost its electron. So therefore you can put water on these fires. And as I said, if you look at the national guidance, the fire service turn up and they put copious amounts of water. And if you look at, which I'll put a link in the presentation, there's been quite a lot of research done by the Fire Research Foundation in America in 2016 and FM Global that looked at the use of sprinklers on these types of fires. And they depending on battery chemistry, etc., because that's quite a key factor, but they're quite effective. They won't put out the fire, but they will control the fire spreading. And if you look at the recommendations through the Fire Protection Association in this country about sprinklers, it's very much not about extinguishing the fire. It's limiting the fire size so you don't get a whole range of vehicles fully involved in a compartment fire. You still have the fire. You'll have quite a lot of shielding because of the sprinklers not being able to get into where the battery is. But it will give the fire brigade a fighting chance to then be able to tackle the fire, and that's what we've got to look at.